We spent the last few weeks talking about stars, and we had to invoke all kinds of great physics last week to understand the end of stellar evolution. We're going to take it to the next level this week. The next level in size past stars is galaxies. We live in a galaxy. The galaxy we live in is the Milky Way, so it seems fitting to start this week by discovering the Milky Way, or following the discovery of the Milky Way, as this beautiful image taken obviously in the southern hemisphere shows. It's not hard to find the Milky Way, this great path of light tilted 60 degrees to the celestial equator that cuts across the sky has been known from antiquity. Understanding what it is a different matter, and that's what we're going to try to figure out in the course of most of the beginning of these clips. And I think it was Galileo who first realized that what this strip of light indicated is that we live in a disc-shaped universe. We are part of a disc-shaped collection of stars. What that means is that in directions perpendicular to the disk, we see a few stars nearby, and then beyond them to the darkness of no stars past. But when we look in the direction of the disk, we see the nearby stars as always, and then behind them we see more stars and more stars until there are very distant stars, too far for us to distinguish their light individually, but we can see the collective luminosity as this brightness of the sky. So what Galileo realized is that we live in a disc-shaped collection of stars. A more systematic study of the shape of the universe was undertaken by Herschel in 1785, and what Herschel did is he divided the sky into a few hundred regions, counted the stars in each region, assuming that the average luminosity of stars was the same in all directions. He drew a map of the universe of this disk shape that we live in, and he drew this map extended in each direction depending on how many stars he found, assuming that the farther the universe extended, the more stars he could see. And his map is here on the right, and the salient point is that he put the sun, which is that brighter dot, in the middle of his universe. The reason that he did this, as I said, this was a scientific study, is that he found that in any direction, if he counted the stars in one direction in the sky and in the diametrically opposite direction, he found about the same numbers of stars. His interpretation: we are not near the edge of the world, else we would see few stars in one direction and more in the opposite direction. We see the same in every direction as its opposite. Therefore, he placed the sun roughly in the middle of the universe. A more refined version of this was carried out 150 years later by Kapteyn, and Kapteyn, using slightly more numerical star counts based on brightness, was able to put a size to the universe, and the disk shape that he had was a flattened spheroid. It was 8.5 kiloparsecs in radius and 1.7 kiloparsecs thick. And the sun was not exactly in the middle. It was offset by a little bit, by 650 kiloparsecs in the radial direction and 650 parsecs in the radial direction, and by 38 parsecs away from the plane, which was the central plane of this disk, about which it extended for about 1.7 kiloparsecs. So this was the universe as Kapteyn saw it in 1922. A few years earlier, Shapley in 1917 took a different approach to understanding the shape of the universe and our position within it. And Shapley was looking at globular clusters. Globular clusters can be found, and are typically found, outside the plane of the Milky Way, this ecliptic plane cut out by this the plane of the center of the disk, which, when you see it in the sky, is the plane of this circle of the Milky Way. In these globular clusters, Shapley found variable stars. They turned out to have been Aurora Lyrae variables. He understood something about the period luminosity relationship for variable stars, so he could measure the periods for these stars, extract from this a luminosity, use that and the observed brightness to measure a distance. And so he could take a few globular clusters and map them in 3 dimensions. And because he mapped them in 3 dimensions, he could see that they are not scattered isotropically around Earth, but rather favor a direction. They are centered on direction towards the constellation Sagittarius, towards a point that he measured to be about 15 kiloparsecs away, and they are they occupy a sphere of radius about 100 kiloparsecs around this central point. So Shapley interpreted that point to be the center of the universe. The globular clusters formed a sphere around it, and other stars that were not part of the globular clusters formed this disk in which the solar system found itself. But that too, he conjectured, would be centered about the same center as the center of the sphere of the globular clusters he found. An interesting observation he found was that no globular clusters were visible to him within 10 degrees of the galactic plane. What we'll now call the galactic plane, the center plane of the Milky Way. He called this the zone of avoidance, and all kinds of theories about how tidal forces would have broken apart globular clusters that strayed too close. So we have these two models of the universe, Kapteyn's model with a radius of 8.5 kiloparsecs and Shapley's model with a radius of 100 kiloparsecs. The sun is either 650 parsecs from the center or 15 kiloparsecs from the center, a large universe and a small universe. Who is right? It turns out that they were both wrong. The truth is somewhere in the middle, and they were both wrong for almost exactly the same reason, though in different ways. What they ignored was the fact that starlight, as it travels through the galaxy, suffers extinction, and this was not known. They knew by the 1920s that there were interstellar gas clouds. Those had been discovered. But in between the known interstellar gas clouds, they assumed the universe was a vacuum and hence completely transparent. It was not until 1930 that Trumpler proved that the interstellar medium, even between the known gas clouds, absorbs and scatters starlight so that stars undergo extinction. And it was only in the 1930s that this became clear, that all stars in all directions suffer extinction when light passes through the interstellar space of the galaxy. How did this, ignoring this, influence the results? Well, when Kapteyn was counting stars, he basically assumed that stars he couldn't see did not exist, but there were stars that he could not see because they were too dim due to extinction, and for this reason, he underestimated the size of the universe. He also was placing the sun much too close to the center, because essentially, if your visibility is limited by extinction, then you will be, unless you're very near the edge, in the center of what you can see. You can see about the same distance in all directions, so there will be as many stars in any given direction as in any other, basically because you can't see far enough to distinguish the edges of the world. And so Kapteyn's distances were underestimated, both for the size of the universe and for the distance of the sun from its center. Shapley, on the other hand, was using known luminosities of variable stars, and so his distance estimates were influenced by extinction in a different way. The variable stars that he saw were dimmer than they actually were. We saw that when we did our homework, measuring distance using an RR Lyrae variable. He measured dim RR variable stars. He interpreted that, because he thought he knew their luminosities, as them being distant, since he was neglecting extinction. And so he thought the globular clusters were farther than they actually were. Therefore, Shapley overestimated distances due to extinction, whereas Kapteyn was underestimating distances due to extinction. The correct answer, as we now know it, is that the sun is about 8 kiloparsecs from the center of the galaxy, and so about half the distance estimated by Shapley, and about almost 10 times, more than 10 times the distance estimated by Kapteyn. We know more about this, and we'll spend the rest of this week figuring out what it is we know about the Milky Way, what it is we know about other galaxies, and what this tells us about the universe in general. So that's our plan for the week. Study the Milky Way, understand where we know why I have been saying the universe, because this is what these astronomers called it, how we know that the Milky Way is not the same as the universe. Then study galaxies as a class, see what we can say about their evolution, their dynamics, their structure. This will lead us into a discussion of exciting topics like cosmic expansion and dark matter, which will set us up for next week's discussion of cosmology. Should be a fun week.